Are you ready for some alcohol reactions? We're generally writing ROH or maybe including that little carbon there. We'll have some restrictions on what R can be as we go through this chapter, which I'll spell out right away. Before I do that, let's start off on a light note. You might see this chemistry cat, it's well known. Usually I think they're cute, but this one I'm not as big of a fan of. Alcohol is a solution, technically speaking. Technically, it's actually not. So you're trying to tell me a bottle of propanol, butanol, ethanol that I find in the lab is going to be a solution? I really hope not. I'm counting on it to be pure if I buy a bottle of butanol. Of course, it's referring to alcoholic beverages. So if you want to get technical, you got to be a little more precise with the language. As Dwight points out, false, not a solution, but beverages are inherently a solution because their base is water. You might even say their solvent is water. The solute, the smaller participant in the solution is usually the ethanol. So solvent and solute. So alcohol can serve as a solvent. It can serve as a solute, but by itself, it's never a solution, ever. So then this other one handles it, kind of, I think, preempts that. So ethanol and water, fine, that's a solution. I'll buy that. So just thought you might enjoy kind of that little divergence into alcohol terminology. When we are reacting alcohols, ROH, or we might write it this way, we will assume the R is pretty much any generic organic substrate other than specifically not allowed are the special hydroxy-containing functional groups that are types of alcohols, but they have their own name because they actually react differently. So when we're learning reactions, we're going to assume that we're not starting with an enol, alkene, with an alcohol attached, or a benzene ring, which also contains CC pi bonds with an alcohol attached, known as a phenol. Thanks to resonance, they just don't react the same way. So you can envision pushing that lone pair out, right? On both of them, that makes them, we know enols go to the keto tautomer, for example, and phenols with that resonance won't have the same. We already know they don't have the same pKa as a typical alcohol, so that has it's an indication that its reactivity is different, right? So we're going to not include those in our list of alcohols that react, but whether you remember or not, we've actually reacted alcohols before. So this little roadmap here is going to serve to remind us of ones we've done, what you already know, what you might not know that you already know. So to summarize this, I had to make it sort of a generic template where we have at least 2 carbons in our substrate. I'll call this alpha, beta. And depending on what was on the beta carbon, we could get a variety of different outcomes. So if we had adjacent or beta to our alcohol, an H, a boring old H, that would allow us to do an elimination reaction, beta H's, right? That means OH needed to be a good leaving group. So to turn it into a good leaving group, we can simply add a catalytic amount of acid. And if we add a catalytic amount of acid, we get acid catalyzed dehydration. Right? So I'll write that out. Acid catalyzed dehydration. Once again, this is just review, so we can keep those at the forefront of our mind. It'll also help us predict what alcohols like to do if we know what some of their reactions already did. Alkene. So we can turn an alcohol into an alkene. What if instead of an H there, we actually had a leaving group? But instead of having acidic conditions, we had basic conditions. So know that when alcohol is in acidic conditions, it becomes water. When it's in basic conditions, it becomes O-. O- is a nucleophile. The nucleophile attacks carbons with leaving groups. So it can, if the carbon with the leaving group is right next to it, it would make an epoxide, as we've seen, right? So another one we have done before. It's another way to arrive at an epoxide is to have a halohydrin for example. And so I might even write there, e.g. halohydrin. We get an epoxide. Epoxides aren't the only thing we can get with that pattern. If it's alpha beta, we would get an epoxide, but we could also say, or larger, because we've done this as well, cyclic ethers. And epoxide is a cyclic ether. It's just this special name for three-membered ring, cyclic ether. If OH and LG are spaced out by more carbons or further away. Because it's simply nothing other than an internal SN2, right? What if it's not an internal SN2? We can have an external SN2. So first we have to turn O into the nucleophile. Base does that, O minus. Then if we have an R group nearby, that's not a leaving group, right? But if we throw in a substrate that has a leaving group, like this one, then we would get an ether that's not cyclic because it attacks something external as opposed to attacking its own tail. So let's redraw this with X equals R now. So that's those three groups on that carbon, on the beta carbon. Now for my alpha carbon, the OH is now an O. It became an O minus in the first step. That O minus attacked, right? So we turn this into, I'll just show after step one. We would have R, 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 O minus. Then draw in your lone pairs. Since it's two steps, I'll draw this mechanism. SN2, right? SN2 for step 2. So draw on the carbon, and that R prime is now there. So we can get ethers that are not cyclic as well. What can we learn from the things we've seen in the past? History will repeat itself. We're going to see alcohol behave similarly, so we might as well learn from that. The OH can either become a leaving group if we add acid, or a nucleophile if we add base. Okay? So we need either basic conditions or acidic conditions. So we have done this for our acid. We've usually chosen sulfuric acid, tosic acid, right? What happens if we use HBr? HX, HCl, HI, HX. It turns out we will not get acid catalyzed dehydration like we would with H2SO4. So in other words, reminder, if this is H2SO4, we get an alkene, right? If this is not H2SO4 and it's HBr, we don't get an alkene. We instead get an alkyl halide. Let's show the mechanism. Why does one acid, changing the acid, make a difference on what the outcome is? Let's take a look. Well, look at that. It's the same first step. In the presence of acid, alcohol is going to be protonated. So it helps to know that we can at least start just about any mechanism that contains an acid, even if it's a different acid you're not used to working with. Well, now this next step is going to be the same as anything we've done before. Now that we have a good leaving group, it's going to leave. Look at that. We have a carbocation intermediate, and it's tertiary. So I stop and think, can it be anything better? Nah, I'm going to keep going. What are the options for going after we know we can't rearrange a carbocation any further? It either eliminates to form a pi bond. That's what happens if it's sulfuric acid, or it captures a nucleophile. That's what happens with HBr. And that makes sense because Br is a great nucleophile. Hydrogen sulfate's not. So attack, and here we are. We can have rearrangements because the carbocation is present. In this case, we didn't. So it's not always just a simple swap out the OH and you get the Rx, but we can remind ourselves that this transformation is possible. With HX, we get Rx. All right, so just a question I asked out loud. Why do we not see this product In other words, a new nucleophile attached. This is SN1 essentially, right? Why do we not see that when we use sulfuric acid or tosic acid? Don't forget what tosic acid is. So sulfuric acid is a favorite acid, especially in general chemistry. Organic chemists love it too. It's a great acid because it's restricted to acting as an acid. It's not a good, its conjugate base is a bad nucleophile. So if you want to control it and make sure you don't get nucleophilic attack of your acid later, the conjugate base of your acid, then this is a great one to choose. Now, tosic acid is sulfuric acid, but replace one of the H's with the toluene. All right, I'm going to write that because students get good about recognizing ionic compounds, and then they start to think this is some sort of element, TS plus, OH minus. That couldn't be more wrong. Because I see that enough, I'm going to put that here. Frown. Don't do that. Don't fall for that. It's just an abbreviation. Okay. TSO is tosylate, essentially, OTS, right? But it's the acid form instead of the leaving group form. So TSO would be this. TSOH would be that. So let's spell that out. This is nothing other than OTS, and then here's our H. HOTS or TSOH, okay? It's called tosic acid. Tosic acid. That's how you say it when you read it. All right. Why doesn't that happen? This results in E1 dehydration because the conjugate base HOSO is too resonance stabilized to be a good nucleophile. So it simply acts as a conjugate base and does dehydration. Okay, let's show a little more practice in what our capabilities are with HX. Okay, so it turns out that if we do this mechanism again, primary alcohol means only one other carbon attached to the alcohol. We still get the alkyl halide. You say, how so? Primary groups, leaving groups, mean we shouldn't have an SN1. And that's because it doesn't do SN1 in that case. SN2 always happens faster than SN1 if it's an option, but since it's not an option, it's going to have to be SN2. So we still have that step, but this cannot leave by itself. So the bromide that just was liberated up there is free to attack. Kick off, same step, SN2. SN2 for primary ROH. So obviously we won't see a rearrangement in that scenario. HCl, turns out this doesn't react very well because it's just enough less reactive that it's very slow in this case. So we have to add something to help it. Okay, so it's no reaction unless we add zinc chloride. This is just, it's an assist. What does it do? It actually helps turn that OH into a very good leaving group. And so we have OH, and it attacks the zinc. Let me draw out the zinc chloride. Oxygen loves zinc. Oxygen loves transition metals. That's why they get oxidized so easily. You leave them out and you get rust or patina or whatever the term is for the oxidized metal. Just the oxygen from the air will interact with it. So zinc is easily oxidized, interacts with oxygen. That oxygen-zinc bond is very favorable. So this is serving as what we call a Lewis acid, not a Bronsted-Lowry acid. So there's a distinction. We haven't seen those in a while. It's strictly a Lewis acid for OH. because look what it does. It acts like it's like a proton does. It makes it positively charged, a better leaving group, and if it leaves, it gets to go off with zinc, and zinc's okay with that. So this, as complicated as it looks, is a lot like water. It's a good leaving group. Okay, so notice that chlorine we kicked off right here. We can draw in our lone pairs because we're actually going to use that chlorine, or now a chloride. Now, the not so great nucleophile is compensated by the fact that we have a great leaving group. And voila, we finally get our alkyl chloride. Okay, so for HCl, you're going to see that additive there, that zinc chloride, to help out. Okay, so I warned you that every time we learn about acid conversions, they're great and easy and cheap, but a lot of other functional groups react with acids, and as we increase our complexity of the substrate, acid might not be an option. So we need to have another route. So another way to make an alkyl halide, specifically in this case, what's listed here is a bromide, but we could also do a chlorination route with what's called SOCl2. So PBr3 or SOCl2. Let me just write that scheme out instead of having it just in words. So these are our acid-free reagents to access RCl, RBr, in other words. Okay. So it's an SN2 mechanism. Nice thing about that is no rearrangement, right? So if you want to make sure there's no rearrangement because it was possible with the HBr, that's another reason to use it. Okay, but it is an SN2, so you got to watch out for the inversion. All right, so how does this happen? Once again, it's called acid-free because it's Bronsted-Lowry acid-free. There's no free proton exchange. However, this is still simply acting as a Lewis acid. So oxygen attacks phosphorus. So PBr3 is here. Here we go. Attack. And then a bromine leaves. And we have our amazing leaving group again. What's left of the PBr3 is now PBr2. Positively charged oxygen. Great leaving group. Now we can have our bromide come in that we liberated earlier. Attack. SN2 style backside attack. That means, watch out. Need to have, since stereochemistry was shown, need to have the new bromine on a dash because it was a wedge before. So watch out for the inversion if it's possible. So chlorination, acid-free, is a little different. In fact, it's in basic conditions because we use SOCl2, but it's a similar idea. So we're going to turn that OH into a great leaving group without using acid. And not only does you might say, why don't we use tosylate or something? And that does turn it into a great leaving group. That would be an extra step because this has the chlorinating agent built in. So it has the chlorine we need, but it also is built into this thionyl chloride, as it's called, to help us get our reaction that we need. So SOCl2 has this Lewis structure. So let's take a look at the mechanism. We're going to be in basic conditions. We're not going to protonate that OH, but it will attack something. In fact, if we look for our most electron poor bond here, or atom here, we can see that there's a dipole, right? So it can attack and open those electrons toward the electronegative atom. Now, we don't usually do a lot of these sorts of mechanisms till 212 where we're attacking an sp2 hybridized atom, but you know, I just want, because this is introduced now, I want you to know how this works, or understand how it works. So O minus Cl Hopefully the logic still makes sense, even though it's a little more convoluted than ones we're used to seeing. Okay, so then what happens is that because that pi bond is favorable and charge is not, it closes again. And in doing so, it has to eject something off the sulfur, and the sulfur chooses to eject the chloride. There's our free chlorine. So put that here, Cl minus, because we're going to use it later. And so now we have closed that pi bond back. It looks a lot like the SOCl2 we started with, except now it has the substrate on one end. We still have that pesky positive charge. Pyridine helps with that. Pyridine's not a strong enough acid to deprotonate an alcohol on its own, or excuse me, a strong enough base to deprotonate an alcohol on its own. So instead, we kind of wait till it gets to this ultra acidic point where it's an oxonium. There we go. Much more willing to come off now. There's the intermediate we have. The chloride comes along finally at this point. Now watch this closely. It's kind of cool. Zoom in. Attack. Because we got to get rid of the O, right? Because we're replacing it with the chlorine. So not only does the bond land on the O is going to share it between itself and sulfur to make a double bond. So I'm going to skip writing that extra step. You're allowed to do that. You can go from bond to atom or bond to bond. You can't go even further because notice that I'm still, even though going bond to bond, I'm still letting oxygen use those electrons. So I didn't skip over oxygen. So bond to bond. So now it's pi bond. This bond's broken. That makes SO2, which is a gas, but not with this chlorine attached. So in that same process, making that extra bond to sulfur helps eject the chlorine and make another chloride. So this is that super rewarding part where SO2 gas is evolved. Yes, you get to draw the gaseous arrow. It's coming out of solution. And now all of that fancy footwork to get us to the Cl. Okay. It is SN2 right here. So if we had a dash or wedge, we would invert it. Since my example here had a primary carbon, then it doesn't go play in there, but you would treat it similar to like you did there in SN2 inversion. Okay. Okay, so with all these SN2 inversions, we might get some little logic problems here. Like, what if we wanted to transform an alcohol into a new group? So in other words, it needs to become a leaving group into a new group, but not have an inversion. What do we need to do? Something that retains, at least net retains the stereocenter. What we could do is do a double inversion. Double inversion is net retention, right? So go from wedge to dash, go back from dash to wedge.